Okay, so last little bit about alcohols then is just their use as biofuels. Um, so just going to quick look at what biofuels are, how we use them. It's not loads of information, but it's just a little bit. And it's sort of like this chemistry and environment stuff. And you'll have done that at GCSE and they pop it in again at A level and they pop it in with organic chemistry because it makes the most sense. Because alcohols are what we use for biofuels. So yeah, we're just going to quickly look at, if it will open to the next page. That doesn't want to. What a biofuel actually is, how carbon dioxide is produced and basically adds to global warming, what carbon neutrality actually is, and then look at some environmental issues of biofuels. So it's that sort of benefits versus negatives, pros and cons of biofuels. It's just a really quick, it's more just sort of information rather than real sort of knowledge or being able to like analyze something. So basically, a biofuel is just a renewable fuel made from plant material. So we use them a lot as we use the term petrol, but as a fuel in our cars. We can use them to fuel vehicles, for example. Unlike things like traditional petrol and diesel, these are renewable. So lots of the traditional fuels like let's use diesel for example, they come from fossil fuels, which obviously are non-renewable, and we know they're depleting. So there's this move towards biofuels. Well, can we get something that's renewable? So we have like electric cars and things, but also biofuels are renewable. So we can use them instead of petrol and diesel. Obviously, you can't just stick them in any car. Their cars have to be made specifically to use biofuel. So an example of a biofuel is bioethanol. It's produced by fermenting the glucose in sugarcane and other crops and basically making an alcohol. It's a liquid fuel that burns really, really well in a similar way to petrol and diesel. However, it can't be used on its own in a normal car engine unless the engine is modified. So you have to then go in and modify the engines. So most petrol engines can use petrol containing up to 10% ethanol without needing any modifications. So what you'll sometimes see is rather than fuels at petrol stations being pure biofuel, they'll sometimes mix them. And that's what you get now. So loads of people sort of freaked out a bit when they brought in this new fuel, and lots of petrol stations are using it already. I think it's what called like E95, I think, or 95. It's something like that anyway. And loads of people were like, oh no, I don't know if my car can use it. And the vast majority of cars can use it. And basically what it is, it's petrol mixed with bioethanol. So it's better than just using pure petrol because 10% of it is bioethanol, so it's renewable. So we're using 10% less petrol. It'd be great if we could use 100% less petrol, but we can't. So that is a benefit rather than just using petrol completely. And those cars don't need any modifications. There's a few cars that can't use it, so people know their car can't use it, so they can only go make sure they have to use the right one at a petrol station now. They can't just put any petrol in. That's basically what biofuel is. So carbon dioxide. So when glucose is produced by photosynthesis, 6 molecules of carbon dioxide are removed from the atmosphere. So when photosynthesis is going on, it removes carbon dioxide from our atmosphere. When we ferment glucose to make the bioethanol, 2 carbon dioxide molecules are produced. So this is possibly starting to show, oh, hang on, is this an issue with biofuels? When we then burn 2 ethanol molecules, a further 4 carbon dioxide molecules are produced. So as you can see, that starts to balance out. And that's where we're going to look at carbon neutrality. Why we're talking about glucose and photosynthesis is obviously because biofuels come from sugarcane, which is a plant, which is glucose. So in that production during photosynthesis of that sugarcane, the plant has removed 6 carbon dioxide from the atmosphere. When we ferment that glucose to make the bioethanol, 2 carbon dioxide molecules are produced and released into the atmosphere. And then when we burn 2 ethanol molecules, a further 4 carbon dioxide molecules are produced. So it's that balancing. So actually we would call that carbon neutral. So basically when we ferment it and then combust it, 6 carbon dioxide go into the atmosphere. But then in photosynthesis, it takes in 6 carbon dioxides. The plant removes it from the atmosphere. So in total, 6 molecules of carbon dioxide are removed from the atmosphere, and then 6 molecules are released. So biofuels are therefore sometimes described as carbon neutral. And that just means that their production and usage leads to no net carbon dioxide emissions into the atmosphere. It balances out. However, it's really simple, and there's actually a lot of other factors we have to take into account when talking about carbon neutrality. It's not actually ever really as simple as this diagram shows, as you could probably guess. So are biofuels actually carbon neutral? So we can have biofuels such as biodiesel and bioethanol. They are renewable fuels and we get them from plants, but are they actually carbon neutral? So let's start off with the plant. So as the plant is growing, the plants, and these are plants that we're going to use to make biofuels, they absorb carbon dioxide from the atmosphere for photosynthesis. Okay, nice and simple. When we then burn them as fuel, they release the same amount of carbon dioxide. Therefore, biofuels are said to be carbon neutral. So although biofuels absorb as much carbon dioxide as they release, it's not actually that simple, because they also require energy input for many parts of the process of making them, all of which will release more CO2. So when we're growing the plants, we need fertilizers, we need pesticides, and then we actually need to spray the biofuel crop. All of this requires energy. All of this producing this releases, this energy releases more carbon dioxide into the atmosphere. When we then go and harvest and process these crops for fuel, this also requires energy, which often comes from burning fossil fuels, and so releases even more carbon dioxide. This, in addition to the carbon dioxide that's released by burning the fuel, gives the argument of, well, are biofuels actually carbon neutral? Are they still a good alternative to burning fossil fuels? So there's no set answer for that. It's just sort of a question. We sort of have to take that into account. Actually, it's not as clear cut as we like, or it's often sold to us. So there's quite a few environmental issues that we have to consider when we decide whether to use biofuels or not. The first one is deforestation, its impact. So these biofuels need to be planted, these crops need to be planted somewhere. And so what often happens is people go and cut down forests to make space for biofuel crops. Obviously that's going to offset that carbon neutrality as well, because we're cutting down loads of plants, possibly more that could be taken in more photosynthesis than the crops could, because it's a monoculture as well. So we've only got one type of crop growing there. So we're losing habitat loss, we're losing biodiversity in that process. And actually during that as well, like I was saying, like if you've got a rainforest, for example, in 1 square meter of a rainforest, you're going to have more plants than a monocrop of sugarcane, for example. It's going to be more abundant, it's going to be more species rich, it's also just going to have more plants there, which are probably going to go through more photosynthesis, which in turn isn't great. Land usage. So the land that we use to produce biofuels could instead be used to grow food crops. So large-scale biofuel production may cause food shortages and increase food prices because we have less land to grow food on. And carbon dioxide production. So biofuels are not carbon neutral. Fossil fuels are used in their production. So to make fertilizers, run the glucose fermentation plant and transport fuels, all those things we were talking about earlier. If we look at the advantages and disadvantages of biofuels, cheap's a funny one. I want to put cheap in the middle for now. Well, it's going to disadvantages, didn't want that. I was going to discuss cheap in a minute. Production often uses energy from fossil fuels. Well, that's a disadvantage. I mean, an advantage is that it's cheap. That's not a disadvantage. Absorb CO2 as they grow. Well, that would be an advantage of a biofuel. They burn well. That's an advantage. They release CO2 when they burn, that's a disadvantage. They reduce biodiversity, disadvantage. Use land that could be used for food crops, disadvantage. The renewable, advantage. That's basically it about biofuels. So what we're going to do now is spend a bit of time looking at exam questions to do with alcohols. And then if we sort of finish that, we might look at the last little bit of AS of this section's, I can't think what the word is, organic chemistry. There we go. So sharing that, but I don't want that anymore. I want alcohols questions. Share. Right, so we did this one yesterday. All right, that should be showing up now. I'm just going to double check. Oops, clicked on the wrong thing. This does happen every now and then. Oops, right, so it is sharing. Okay, so that's the one we did yesterday. Here we are. So did not want to draw on that. Yeah. Okay, so glucose can decompose in the presence of microorganisms to form a range of products. One of these is a carboxylic acid. It's got molecular mass of 88 and it contains 40.9% carbon and 4.5% hydrogen mass. So this question asks you to deduce the empirical and molecular formulas of the carboxylic acid formed. So let's just make that. I don't know what is going on. Right. Okay. So let's have a look of our percentage of oxygen by mass. So what have we got? So we've got our carboxylic acid. Glucose can decompose in the presence of microorganisms to form a range of products. Okay, so we need to know our empirical formula. So our empirical formula and then our molecular formula. So we're going to deduce the empirical and molecular formulas of the carboxylic acid formed. So we're starting with glucose. So obviously C6H12O6. So we're going to get our percentage of oxygen by mass. That's the first thing that we want to do. So we're going to start off with 100. And because we've obviously been given our mass, well, we've got our percentages here. So we know our mass of carboxylic acid is 88. We know 40.9% of that is carbon. And we know 4.5% of that is hydrogen. Obviously, the only other atom that we now need to know about is oxygen. So if we start here, I don't really feel like this is going to give me enough space to write it all, but let's go with it. If I need to rub things out, I will. So obviously this is done in percentages. So 100% over here. So we've got our 100%. And all we're going to do simply is, I'm hoping I've got a calculator. There we go. Got my phone now. We're going to take off the percentages from this. So carbon dioxide is 40.9. So we're going to do 100 minus 40.9, and we're also going to take away from it 4.5. So 100. Let's do that one. Let's get a calculator up. It's probably the worst idea to try and get a calculator up, but there we go. Who knows what screen share showing now? No, it is trying to show the graph. Let me give up on that for a minute because that is not working. So 100, we're going to take 40.9, we're going to take 4.5. That's going to give us 54.6. And that is going to be our mass of a percentage of oxygen by mass. So percentage of oxygen by mass is 54.6%. So now we just need to work out the actual mass of each of them. So we also need our relative atomic mass for each one. So if we're going to look at carbon first, so we're going to do for carbon, I'm just going to put each name of each molecule above all the letters. So we've got carbon, we've got hydrogen, and we've got oxygen here. What we're going to come along and do is we're going to try to divide all of them by their atomic mass. So carbon is going to be divided by 12, and that will give us 3.41. Hydrogen, we're going to divide obviously by 1, which will give us 4.5. And then oxygen, we're going to divide by 16, which will give us, what is that, 54.6? 54.6 divided by 16, 3.41. So that is our smallest. So that is this is basically, so now we need to get our empirical formula from this. And we're going to divide everything by the smallest. So that is our smallest one. So that's our smallest unit. And our smallest unit here is obviously the oxygen. So what we will do is we do 3.41 divided by 3.41. Obviously it would give us 1, which will tell us there's 1 oxygen molecule. 4.5, we're going to divide that by 3.41, and that's going to be 4.5 divided by 3.41, 1.32, and then 3.41. I'm going to divide by 3.41. Have I got that twice? Yes, it's obviously going to be 1. So our nearest whole number ratio is 1 to 3. So our nearest whole number ratio is 1 times 3. Here, so that's our whole number ratio. So basically our ratio that we're going with here is, because we've got 4 molecules in total, so we've got 1, 2, 3 here, a 1 to 3 ratio. So we're going to stick our ratio in. So our ratio would go 3 to 3.96 to 3, because obviously that would be, if we did 1 times 3 is 3, 1.32 times 3 is 3.96, and then 1 times 3 is 3. So I'm really annoyed because that's going to, if we remember that, I'm just going to write that down. I'm going to have to rub some of this out now, which is really annoying. I thought I had more space. Okay, so we got to our ratio. So I'm just going to pop carbon, hydrogen, oxygen. And I'd got to the point where I said, okay, well, we've got 3.9, what have I wrote? 3.96 and 3, because I times the 1 by the, well, I've done 1 times 3, 1.32 times 3, and then 1 times 3. So we now need to do our nearest integer ratio. So that would be our ratios here, but we can't obviously do a ratio with 0.96. So our nearest whole integer ratio would be 3 to 4, 3. So our empirical formula in this situation would therefore be C3 H4O3. And then the last bit we need to do is our molecular formula. So our empirical formula mass is 88. Therefore, our molecular formula is going to be exactly the same as our empirical formula, because our empirical formula mass and our molecular formula mass are exactly the same. So therefore, it's going to be the same. So that would be C3H4O3. So ethanol, as we've discussed, is formed by the fermentation of glucose. So a student carries out this fermentation reaction in a beaker and uses an aqueous solution of glucose at a temperature of 25 degrees in the presence of yeast. And all it does is ask you to write an equation for reaction during fermentation. So it's fermentation of glucose. So first thing you want to do is just write out glucose, which obviously is C6H10O6, and you should know that really off by heart now from GCSE because you've used it so many times. And it forms ethanol and carbon dioxide. So carbon dioxide we're going to pop here as CO2.
Hello, Rebecca.
Hi.
There isn't any screen. Sorry, just the blank white. Yeah. So I was just wondering, how to interrupt you. I was just waiting it will come. So, but still,
you see it now?
No, just the blank white. Yeah, now it has come out. Yeah.
Can you see the writing now?
Yeah. Because
fab.
it has been 2 minutes like that, but I thought it will come we were just waiting for the thing.
I'll go back to the other one again in a second so you can see what I've written. Yeah. So can you see everything now?
Yeah. Now it has come out. Yeah.
I don't know what happened there. Okay, so yeah, so we've got so we've got glucose. We've got our carbon dioxide, and obviously the other thing that we need is our ethanol. We're obviously going to need to balance this at some point, but let's just pop our ethanol in first, which is C2H5OH. So that's the important bits that we know then. And then we just need to double check the balancing. So I'm going to oversimplify the balancing and make it really simple. I know you probably know how to balance, but just double check. So obviously we've got 6 carbons on this side. On our product side at the minute, we've only got 3 carbons. Hydrogens at the moment, we've got 10 on one side and we've only got 5 on this side. And why have I wrote 10? C6, it should be H12, not H10. Why have I wrote 10? H12. So we've got 12 on our reactants and 5 on our products. And oxygen, we've got 6 on one side, and then on our products, we've only got 3. So we need to balance this up. First thing we're going to deal with is hydrogen. It's the easiest one. I know we haven't got 5, we've got 6 on this side. This is why you should double check what you're doing. Because obviously we've got 5 there, but we've got the OH. So yeah, we've got 6 on this side. So yeah, first thing I'd say is balance your hydrogens, because hydrogen's only present in the ethanol. And then we can deal with the carbon and the oxygen afterwards. So we've got 12 hydrogens in our reactants, 6 in our products. So basically we just need 2 molecules of ethanol. So if we stick a 2 in front, let's have a look at it now. And we've got C6H12O6. We've now got 12 hydrogens. We've now got 1, 2, 3, 4, 5 carbons, and we've got 1, 2, 3, 4 oxygens. So now we just need to finish balancing off the oxygens. We just need 2 more oxygens, 1 more carbon. So the easiest thing would be just 2 carbon dioxide molecules. And there you go. That's it, balanced. I know that's really simple, but I just thought I'd quickly go over how to do it really simply, just in case. Yeah, I'm going to get back to this question really quickly, just to go through what we were doing, because it went blank. So I apologize about it going blank. I've clearly clicked on something. I was trying to get to, I know what happened. I was trying to get a calculator to load and it all just went wrong. So that's why you don't try and use a calculator. So yeah, this question, they sort of throw these ones in all over the place. It's basically glucose can decompose and form a range of products. One of these products is carboxylic acid, and we've given the mass of that. Well, its empirical formula, which is 88, contains 40.9% carbon, 4.5% hydrogen mass, and it wants us to get the empirical and molecular formulas of the carboxylic acid that's formed. So first thing to do, I always set it out like this. I'm just going to put my carbon over here, hydrogen here, and my oxygen here. So we need to know how much oxygen we've got. We don't know at the minute. Well, we can work it out really quick, because if we've got 100%, 40.9% of that is carbon. So we'll take that away. Also take away 4.5%, because that's our hydrogen, and whatever will be left will be our carbon, will be our oxygen, sorry, and that would be 54.6%. So that's how much carbon we've got, how much oxygen we've got in percentage of mass. So now we're going to divide all of them by their atomic number. So carbon is 40.9. I'm going to divide that. That is not a divide symbol. We're going to divide carbon and divide carbon by 12, and that will give us 3.41. Hydrogen, do exactly the same. That's 4.5 in its percentage mass. Obviously, 1 is its AR, so that will give us still 4.5. The oxygen we just found is 54.6, so we're going to do 54.6, divide that by 16, and that will give us 3.41. Now we just need to work out the ratios. When we're doing this for ratios, we divide everything by the smallest. So we've got 2 that are 3.41. So we're just going to divide everything by 3.41. So we do 3.41 divided by 3.41, which obviously equals 1. And I'll do the same here, so I don't have to write it again. So that 1 equals 1. And that leaves us with 4.5 needing to be divided by 3.41, which gives us 1.32. So this basically is giving us our ratios to get our empirical formula. So our nearest whole number ratio, so to find our nearest whole number ratio now, obviously we've got 3 numbers here. So we're going to multiply everything by 3. So 1, 2, 3, multiply it all by 3. So we're going to do 1 times 3, which will give us 3. 1.32 multiplied by 3. And that's going to give us 3.96. And then 1 times 3 again, which obviously will give us 3. So our ratio at the moment, I'm going to do it in different colour so we can see, would be 3 to 3.96 to 3. Doesn't help us for, well, it will help us for empirical formula, but we can't leave it at that, because we need integers, whole integers. So we're basically going to take that, we're going to round that to the nearest integer to get a nearest integer ratio. So our nearest integer ratio would be 3 to 4 to 3, which makes sense because we're just going to round 3.96 to that. So by doing that, that's basically telling us the empirical formula is 3 carbons it's C3, it's got 3 carbon atoms, H4, 4 hydrogen atoms, and O3, 3 oxygen. Our empirical formula mass, if we add all of that up together, which would be, what have we got? So that would be carbon. We've got 3 lots of carbon, which is 12. So 12 times 3, 36. 4 hydrogens, so plus 4, 40. And then 3 times 16, 48. So 40 plus 48 is 88. So our empirical formula mass, so the mass for our empirical formula is 88. We've already been told that our molecular formula is 88, which means that our molecular formula then is identical, C3H4O3, to our empirical formula. It is a 4-mark question, so you do get a lot of marks for it. I'm just going to quickly tell you where you get the marks for each bit. I don't know why it gave such a tiny writing space, because it is a 4-mark question. There's a lot of maths to it. So you get, basically, you would get 1 mark for working out the percentage, the mass in percentage for the oxygen. You'll get 1 mark by dividing everything by its atomic number. So then we would get these numbers. So basically like the 40.9 divided by 12. So this first top row of workings out I did, you get a mark for that. You would then get a mark for working out the ratio, but this ratio to the integer. So then all this next bit is just working out the ratios. So then you get another mark for working out the ratios, because obviously that ratio will then give you your empirical formula. So it's basically the ratio, because that gives you the empirical formula. So mark 1, mark 2, mark 3, and then your 4th mark is for giving your molecular formula. So that's where all 4 marks come in. So yeah, so we've just looked at ethanol being formed by fermentation of glucose. So that reaction is C6H12O6, gives us 2 molecules of ethanol and 2 molecules of carbon dioxide. In industry, the fermentation is carried out at 35 degrees rather than 25 degrees. And what you're asked here is just to suggest 1 advantage and 1 disadvantage of carrying out the fermentation at this higher temperature. So if we think about it, what's an advantage of doing it at a high temperature? Well, you're going to produce the ethanol quicker. So our ethanol is produced more quickly. We know the hotter something is, it speeds up the rate of reaction. We heat it up higher, the ethanol is going to be made more quickly. That will get you your 1st mark. 2nd mark is just for stating disadvantage. By heating up more, we require more energy, so more energy is required in reaction. So more energy is required for reaction, which obviously would then add to the carbon dioxide being released, costs more. You don't need that. It just basically wants ethanol to produce more quickly, more energy is required, and that's all you need to state for that, and that would get you the whole 2 marks. So the method used by the student in part B would result in the ethanol being contaminated by ethanoic acid. So the method used by the student in part B would result in our ethanol being contaminated by ethanoic acid. So let's have a look at that method again. So ethanol is formed by the fermentation of glucose. Student carried this fermentation out in a beaker using aqueous solution of glucose in the presence of yeast. So how does this contamination occur? Well, how did they do it? Well, ethanoic acid. So if we think about alcohols, alcohols can obviously get oxidized and then refluxed into forming carboxylic acid. So ethanoic acid is a carboxylic acid. So we're fermenting glucose in a beaker, and basically what's going to happen is air's going to get into oxidation is going to occur. It's going to be a form of oxidation. So it's that knowledge again of alcohols applying that oxidation is going to occur. So how does the contamination occur? Air gets in. So oxidation occurs, and that would get you the whole mark. So that whole question, I think, oh, is that the whole of that question, or actually have we got more of that question? No, we've still got a bit more to that question. So it's quite a long ongoing question, this one. So this then goes back to really early stuff that we did in chemistry. So infrared spectrum, IR spectrum. So if you can't remember IR spectrum, it might be a good chance to maybe look back at that if you're thinking, I can't remember what the infrared spectrum is, but I can quickly cover a bit of that next week. It's basically just one of those ways that we can look at the differences of molecules. So it's asking us to give two differences. So that's really important. Two, and it needs to be differences between the infrared spectrum of carboxylic acid and that of an alcohol, other than in their fingerprint region. So that's that main area. So basically, it just wants us to point out what's going to be different about them. So we've got a carboxylic acid, we've got our alcohol. So our alcohol OH absorption, so they've both got an OH group in them, but they're going to absorb the infrared in different places where the OH group is. So alcohol absorption, OH absorption is going to be in a different place. So our alcohol, you don't need to know the numbers for this. OH absorption in a different place. And I would always put to the carboxylic acid. Was it carboxylic? Yeah. I'm just going to put Ca to the carboxylic acid, so you know what you're referring to. Second difference is we've obviously got that C double bond O in our carboxylic acid. So the C double bond O in acids has a different absorption rate. Absorption acids, and well, it has we don't have oxy in alcohol. C double bond O in acids has an absorption. You should know this one. It's an absorption of anything between 1680 to 1750 centimeters. And so that whole question in total would give us 10 marks. Alcohols can be prepared from alkenes in various ways. So this is that opposite. So you know how we were saying, oh, we can turn alcohols into alkenes. We can make alcohols from alkenes as well. So one way is on a laboratory scale, and we get a mixture. And let's have a quick look what I mean. So we're making alcohols from alkenes. So on a laboratory scale, we can get a mixture, that's an important word, of propan 1-ol and propan 2-ol, and it can be prepared from propene in 2 steps. So in step 1, our propene reacts with cold concentrated sulfuric acid to form intermediate compounds. That's quite important, that part. Step 2, our intermediate compounds react with water to form the mixture of alcohols, because obviously we've got the 2. What the question wants you to do is this: name and outline. So we need to say what it is and outline the mechanism for the reaction between propene and concentrated sulfuric acid to form intermediate compounds, which gives propan 2-ol in step 2. And it wants you to explain why propan 2-ol is a major product of this preparation. So let's have a quick check how many marks this question is. It is a 7-mark question. So what is going on? Straight away, let's have a look. First thing it wants you to do is name. So name and outline the mechanism for the reaction between propene and concentrated sulfuric acid. So if we remember from yesterday, that is a form of electrophilic addition. So we've got the propene, we're going to have those electrophiles being added to it, and we're going to form from the sulfuric acid. So the sulfuric acid is going to act as that electrophile and get them intermediate compounds, and we're going to get propan-2-ol. So first mark, even if it's anything you wrote, is if you say it's electrophilic addition. I'm going to just write it. Yeah, I'm going to write it down here. So yeah, I'm going to pop this here. So we've got electrophilic addition. I'm going to mark that here, and that's the first mark, electrophilic addition. So we've named the mechanism. Then you get marks for outlining the mechanism. Now, I'm just going to double check on that scheme how many marks you get for each little bit, because it's a 7-mark question. So you can actually get quite a lot for drawing the mechanism out. So let me just double check this. 1, 2, 3. So you get 4 for outlining the mechanism. So again, 1 for the name, 4 for outlining the mechanism, which will take us to 5, and then 2 marks for explaining why propan-2-ol would be our major product of the prep. So let's have a go then at drawing this out. So let's draw out, what is it that's reacting together? Propene. Let's draw propene first. I'm going to draw propene all the way over here. Propene, we've got, I'm going to draw a double bond in first. Carbon-carbon double bond. Just makes it easier because remember we've got an alkene, so we've got that double bond. Propene, we've got 3 carbons, so we're going to have a H3C up the top. That's going there. And then obviously we've got another hydrogen down there. So that's our propene drawn. Next thing I'm going to do is I'm going to draw sulfuric acid out. So again, you need to know how to draw sulfuric acid. I'm just going to talk sulfuric acid out through with you quickly. So this is something that you just need to learn. So we've got our sulfur here. We have a double bond to an oxygen at the top, double bond to our oxygen at the bottom. Have an OH here, and then an OH on the other side. Now I'm going to draw onto here positive and negative sides on our signs, charges onto our hydrogen and oxygen. So here, obviously, our oxygen is going to have that slight negative charge, which allows it to have this electrophilic addition going on, and our hydrogen is going to have that slightly positive charge. So what is going to happen is, because, as we've said before, because of the electron density around that carbon-carbon double bond and that slight electronegativity of the oxygen and that positivity of the hydrogen, because obviously sulfuric acid, as we said, it's a polar compound because of that OH group. We've got that electron density up here. What is going to happen is the carbon-carbon double bond is going to break, and an electron is going to come here to hydrogen because of that positive bond. Bond's going to break, electrophile is going to work that way to the hydrogen. Because of that happening, the bond between the hydrogen and the oxygen is going to break, and that electron is going to come here to the oxygen. Pausing there before I'm going to go straight on to the next step, and then I'm going to talk you through where the marks are. So then we go to our next step. Let's draw our, what's it asking us to draw? Name and outline the mechanism of reaction between propene and concentrated sulfuric acid to form the intermediate compound, which gives propan-2-ol in step 2. Okay, so we now just need to draw the intermediate. We don't need to draw the propan-2-ol out. So that is fine. So that's basically our carbocations that we're going to start drawing out now. So let's get that up. So what has happened here? We've now got our intermediate, we've got our carbon to our carbon. Just now got a hydrogen here because we've got rid of that double bond. So we've got the hydrogen there. And obviously that hydrogen has come from that sulfuric acid. So that's come joint up here and we've made that bond there. We've got hydrogen still that was originally there, hydrogen that was originally there. CH3 up here and hydrogen there. Obviously, we've still got that ability for this carbon now to have another bond with something because we've broken that bond there, so it doesn't have 4 bonds on it, which obviously is going to happen. That's our intermediary. And then obviously our sulfuric acid, so that is that ion now. That's going to come in and that's going to work. So what's going to happen now is I'm going to draw this out and we've got as it would look. So we've got our oxygen double bonded to our sulfur, double bonded oxygen, oxygen, hydrogen, and obviously we've got that lone pair now on our oxygen. Make sure you draw that lone pair on and you've got that negative line above it. Then, as we know, we just need to draw that curly arrow now going up to this carbon. We don't need to draw the final product. That's all we need to do there. Okay. I'm just going to talk through where the marks are for this part and then do that last little bit, which will then explain why propan-2-ol is the major product. So second mark. So we've got our first mark here. Our second mark is going to come from our curly arrow from our carbon-carbon double bond towards the hydrogen of the hydrogen and the oxygen on your sulfuric acid that you've drawn. So basically this curly arrow, so that will get you your second mark. Your third mark would be a curly arrow to break the hydrogen and oxygen on your sulfuric acid. If you haven't got the correct charges on there, you would be penalised for them. So you don't get a mark for them, but if you've got the wrong charges or you don't have them, you would lose a mark. That's out there, number 3. Mark 4 is drawing your intermediate. So, and then mark 5 is going to be your correct anion lone pair incorrect. So this is your intermediate. So you're going to get mark that. And then mark 5 is a correct anion lone pair on the correct oxygen. So obviously it needs to be the correct oxygen. You can't start putting your lone pair onto this oxygen. It needs to be on this one here. And the curly arrow from that lone pair to the positive carbon on the carbocation, which we've got there. So that'd be our 5th mark. I would actually have missed something out. You don't have to have it on, but I would always put it on. I would put on a little positive charge on your carbon here, just to make it clear that that's a carbocation now. We've got our intermediary, got our carbocation. 5 marks we're at. If you'd put a product on it, it would be ignored. You would get 0 marks for your product because you're not asked to draw the product. You're just asked to name and outline the mechanism of reaction between propene and concentrated sulfuric acid to form the intermediate compound. So that is all you needed to do. So that's marks 1 to 5. Then the final part of that is explain why propan-2-ol is the major product of this preparation. So let's have a quick look then. So our major product is propan-2-ol, and that is because it is formed, as we've talked before, whenever we do any of these electrophilic additions. So propan-2-ol is our major product because it is formed from the most stable from the most stable carbocation. That will get you 1 mark. And your final mark is going to explain why that carbocation is more stable. So that is a secondary carbocation, as we can see. The other one would give us a primary carbocation, and a secondary carbocation is more stable than a primary carbocation. So propanol is a middle product because it's formed from a most stable carbocation. This is a secondary carbocation, so I'm just going to put 2 in a degree sign because that's for secondary. So this is a secondary carbocation, which is more stable than a primary carbocation. So continuing this question, what have I done? What have I done here? Let me have a look. I've made it really small. On an industrial scale, ethanol can be produced from ethene by direct hydration or from glucose by fermentation. What has happened to this? Drawing lines all over the screen now. I'm not quite sure what's happening anymore. State the conditions for the direct hydration reaction and state 2 advantages and 2 disadvantages of the fermentation method compared with the direct hydration method. So let's highlight the key parts of this. So industrial scale, that's important. We're making ethanol still. Can produce from ethane by direct hydration or from glucose by fermentation. State the conditions. So this is important. Conditions for direct hydration. And then we need 2 advantages and 2 disadvantages of a fermentation method compared with the direct hydration method. In total, how many marks is this question? This question's worth 6 marks. So first thing you're going to do is do the first part. State the conditions for direct hydration reaction. So the conditions for direct hydration reaction are, and there's 2, and you'll get 2 marks for both of them. The first one is a hot or high temperature or pressure. It will let you say pressure. Please don't put pressure. Well, you can, but temperature is better. If you give an example of a temperature, it will be allowed, but actually it's better to just say a high temperature, a hot or high temperature. So they are a high temperature, and that will get you 1 mark. I'm going to pop that on there. And the other one would be industrial scale ethanol produced by ethane, direct hydration, is the presence of a phosphoric acid catalyst. So presence of phosphoric acid as a catalyst. So a presence of a phosphoric acid catalyst. Just going to finish this question. So, so that would be your first 2 marks. So, and you get your first 2 marks from stating the conditions for direct hydration. So big tick on that. We've done that part. Okay, so now 6 marks. So you can probably see where the next 2 marks are going to come from. 2 from advantages, 2 from disadvantages of the fermentation method compared with the direct hydration method. It's not asking you to discuss them. It's just asking you to state 2 advantages and disadvantages. So you can literally say, this is an advantage, this is a disadvantage, and you don't need to go into it, but you don't need to sort of justify it. You don't need to come to a conclusion. It's just stating them. So an advantage of 2 advantages of fermentation compared with direct hydration method. So An advantage of fermentation. This is quite an obvious one if we think about the conditions for direct hydration. So an advantage of fermentation is it occurs at a lower temperature, so less energy is used. That would give you 1 mark. That's one advantage. There's 2 other advantages you could do. I'm going to come out with the one that I would see most often. I think is the most logical one to come up with. You could link it to the conditions of direct hydration and say there's less equipment needed, or there's less use of non-renewable fuels. So either of the 2. So I'm going to put both on here. And you could get a mark for either. So an advantage of fermentation, it occurs at lower temperature. Also, you need less equipment, and that would get you 1 mark. Or you could also say equipment, or you could say needs less fossil fuels. So there's a potential 3 answers there, but the maximum you can get for saying the advantages is 2 marks, obviously, because it's only asking you to do 2 advantages. So 2 marks for that. We've done that. Last bit of this question, and then we are done for today, is the 2 disadvantages. There is actually 5 disadvantages, so I will fly through them really quick. I'm going to come out with the 2 most obvious ones. First, if it's going to happen at a lower temperature, straight away, disadvantages is slower. Advantage is fermentation is slower. That will give you 1 mark. Just going to list through now the other potential 4 that you could give. Another option is it's got lower atom economy. So it's got low atom economy. You produce impure products. It's difficult to automate. So it's more people intense, it will take longer, cost more. Difficult to automate. And then the last one is obviously that land use of sugarcane. And that would obviously give you the last 2. Fab. Right. So I will stop there for